Okay, so we have already known there are basically two types of plasma. One is the thermal equilibrium plasma, and the other one, another one is the non-equilibrium plasma, and it is also known as the cold plasma, cold non-equilibrium plasma. Okay. So in nature and in the universe, there are thermal equilibrium plasmas. In industry and in the lab, when we design a plasma, usually we use electrical field to accelerate electrons and then generate a plasma by the electrical discharge. And this type of plasma will be a non-equilibrium cold plasma, non-equilibrium plasma or cold plasma. So last week we have already seen this slide. So if we apply an electrical field in a system and there is an electron, so the electron will be accelerated by the electric field, but travel at the direction against the electrical field. So after the electrons have traveled for a certain time period, T, the electron will gain energy from electrical field. So the energy equals to the electrical field times the charge of electron and times the time and the square of this amount divided by 2 times the mass of electron. And in the same electric field and within the same periods of time, cation will be also accelerated by same electrical field and gain this amount of energy. But from these two equations, we can find out here the mass of ions is around 1,000 times of the mass of electron. So that in the same electrical field, the electrons will gain much more energy than the ion does. Okay. So basically, when we apply an electrical field to generate plasma, the most important thing is to control the energy of electron. Control the energy of electron. And in a plasma state, there are different particles. So these particles all exist in the same system or in the same volume. So that once the electrons move, the ions will also move. So electrons and ions appear simultaneously. So if we accelerate electron in some way, the ions will also be influenced because of the electrostatic field. But later on in this chapter, we will see the distance between electrons and ions. The distance will affect the interaction of electron and ions. So when the electron and ions are close enough, shorter than the pi length, the electrons and ions will attract each other. But if electrons and ions are far away, larger than the pi length, then the electrostatic field will not influence the motions of electrons and ions. Okay, so in a plasma state, usually when we consider the phenomena or behavior of plasma, we have to know the scale we're concerned about. So if the scale is larger than the pi length, then it's in a real plasma state, so that electrons and ions move almost freely. But if we look at a scale smaller than the pi length, the electrons and ions will still attract each other. Okay. So if we generate a plasma by electrical field, we actually need to control the energy of electron. Okay. So in a plasma, if we are at the beginning of filling the system or the tube, quartz tube, with certain types of gas. So for example, if we fill in argon gas in the quartz tube, right, and apply electrical field between cathode and anode, And if this field is high enough, and then the electrons can be accelerated to a certain amount of energy. So when the electron with such high energy meet neutral atoms in the gas phase, they might induce an electron impact ionization. And this reaction is very important. So this reaction tells how a neutral atom be ionized by electron. So in this equation on the left side, this electron is called primary electron. Primary electron with high energy. So when the primary electron collides with an atom, it will ionize the atom. So once the atom is ionized, it will form a cation and an electron. And this electron is named secondary electron. Secondary electrons is knocked out from neutral atom. Secondary electron, okay, and with certain energy. And the primary electron lost energy to the electron impact ionization, right? So it will become an electron with less energy than primary electron. And after multiple collisions, the electron energy will achieve an ultimate electron energy. So basically, in an electrical discharge, there are different electrons, primary electrons, secondary electrons, and some ultimate electrons. So actually the energy of electrons are different. Okay. But in the plasma physics, the scientists try to figure out how the electron energy distribution looks like. So later on we will see in theoretical prediction of electron energy distribution, okay, in a plasma. And last week we have already seen this figure. So this figure tells us how much energy is required to ionize the inner gas. So for example, for helium gas, the threshold energy is about 25 or 26 electron volt. So the primary electrons need an energy higher than 25 or 26 electron volt to undergo the electron impact ionization of helium atom. And for argon, the energy is less. The threshold energy is less. So for the argon ionization, the primary electron needs to have a high energy higher than 15.7 electron volt. 15.7 electron volt. Okay. So if you also draw a curve for the electron impact ionization for hydrogen atom, the threshold energy will be around 13.6 electron volts. 13.6, and the energy is equivalent to the ionization energy of the hydrogen atom. Okay, so this figure tells us these phenomena, and the important thing is the threshold energy, and then there's an optimal regions for successful electron impact ionization. Okay, so if the primary energy, the energy of primary electron is smaller than the threshold energy, then the gas cannot be ionized. So you cannot generate plasma. You cannot generate plasma. And if the primary electron energy is too high, if it is higher than 2,000 or 10,000 electron volts, and again, the successful probability of electron impact ionization becomes smaller. So only in these certain regions, right, the probability of electron impact ionization is high enough to generate plasma. Okay, so once the plasma is generated, you can characterize the plasma. So here are a few parameters you like to know. So the neutral atoms, the ions and electrons, and their velocity, their travel velocity, and their energy. And the energy is represented by either electron volt or absolute temperature. So in a typical non-equilibrium plasma generated by electrical discharge, the electrons has energy around few electron volts. So for example, if the energy of electron is 2 electron volts, we can calculate that it is equivalent to a temperature of 23,000 Kelvin. Around 23,000 Kelvin. And for the ions, the energy is much less than the electron in such kind of plasma. So the energy is around 0.04 electron volts, or equivalent to around 500 Kelvin. And for the neutral atoms, neutral gas atoms, the energy is around 293 Kelvin, or equals to 1/40 electron volt. So this is a typical plasma in a positive column. So later on in the next chapter, I will introduce the different regions of plasma in electrical discharge. So from cathode to anode, there are different regions of plasma. Okay, and usually people use positive column to run the plasma enhanced chemical vapor deposition process, and use cathode region to run sputtering or etching process. Okay. So in order to describe a plasma, one needs to know the electron density, ion densities, and neutral particle densities, and the degree of ionization. Because at the beginning, we fill in a system with gas, so that we have a gas density or neutral density. And then you generate a plasma. So a small percentage of the gas are ionized, right? And the ionization will generate electrons and ions. And if the ions are monovalence, then the density of electrons equals to the density of ion. Okay. But if you have an ion which can be a divalence or monovalence, then the number or the density of ion and density of electron will not equal. But if you have the monovalence, the ions, for example, hydrogen, right? Once hydrogen atom is ionized, it forms proton. Right? Proton is only a monovalence. So the density of electron and density of the proton, is equivalent in hydrogen plasma. Okay. And only a small percentage of the neutral species become ionized in a non-equilibrium plasma. So the degree of ionization is also an important parameter or property of plasma. So the degree of ionization equal to the density of ion divided by the sum of the density of ion and the density of neutral. The sum or the number of ions and number of the neutral species. Okay. So for thermal equilibrium plasma, the density of charged species like electrons and ions and the temperature of plasma and the degree of ionization are related. They are related in thermal equilibrium plasma. But in non-equilibrium plasma, these parameters, we need to know all these parameters to describe the property of plasma. So including degree of ionization, the density of charged particles, and then 3 temperature, right? For electron temperature, ion temperature, and neutral gas temperature. And besides, we also need to know electron energy distribution function. So actually there are different electrons inside the plasma. And after multiple collisional process, the energy of electrons will become distributed with a certain function. We can use certain function to describe the energy distribution function, F of E. Okay. And for the non-equilibrium plasma, electron temperature is much higher than ion temperature, and higher than the neutral gas temperature. And for thermal equilibrium plasma, electron temperature, ion temperature, and neutral gas temperatures are equal, are the same. Okay, so this tells a big difference between equilibrium and non-equilibrium plasma. And the degree of ionization of plasma depends on the system you generated. Okay, so some of the plasma might have very, very weak ionization. So the degree of ionization might be 10 to minus 10. And some plasma could be fully ionized if you apply a certain, use the electrical field and a certain arrangement of magnetic field, or use microwave, use wave, and a certain distribution of magnetic field. You might get a plasma with fully ionized. So industry also try to make a fully ionized plasma or high density plasma for certain purpose. Okay. Okay, and last week we have already seen this figure. So the horizontal axis is the pressure of your system, and the vertical axis is the temperature of electrons and temperature of neutral gas in electrical discharge or glow discharges. So if we generate a plasma with low gas pressure, we always get non-equilibrium plasma. So in non-equilibrium plasma, the electron temperature is much higher than the gas temperature. Right? So for example here, the electron temperature is around 2 electron volts. Right? The 2 electron volts is equivalent to 23,000 Kelvin. It's very high, okay? But for the gas temperature, it's only 1.02 electron volts. So the gas temperature is lower than 500 Kelvin, or even around room temperature. So there's a big difference between electron temperature and the gas temperature. Okay, and then if we increase the pressure in our system, the electron temperature will start decreasing, and gas temperatures will start increasing. So around this range, 1 to 10 torr of the gas pressure, we can find out in this region, the change of temperatures become very, very obvious. And then above 10 torr, the electron temperature and ion temperature become very close to each other. So above 10 torr, if you generate a plasma by electrical field, electrical discharge, and the pressure is above 10 torr, you start getting equilibrium plasma. So it will reach a somewhat equilibrium state. Okay. So there are different range of operating pressure and different type of plasma. And usually in industry, when we make the thin film coatings like plasma enhanced chemical vapor deposition, or when we run the sputter deposition process, we always generate the plasma at low pressure. So we use cold plasma or non-equilibrium plasma for a lot of material processing, right? But if you want to use plasma to fuse material together, or to cut material, or to melt material, you need a plasma with very high temperature, high gas temperature. So you can operate or generate plasma at a pressure range close to 1 atmospheric pressure. Okay, so there are different plasmas and the different applications. Okay, so this figure and the next figure, okay, tells us how to distinguish the plasmas. So in physics, in plasma physics, if you study a plasma, first you need to know the density of plasma and the electron temperature of plasma. Okay, so in this figure you can see that there are different kinds of plasma. And in our class, we focus on this region, glow discharge, or non-equilibrium cold plasma, in this region, glow discharge. Okay, and at the beginning of class, we have already seen that the sun. The sun, right? So at the center of the sun, there is a nuclear fusion reaction. And nuclear fission reaction generate an enormous amount of energy. So all the gas species can be ionized by the thermal energy. But in different regions, the thermal energy or the temperatures are different. So the gas will also form a different kind of state. And the outer the surface of the sun, there is a layer of corona. So corona is also one type of plasma. So in this figure, we can see in this figure, we can see that here is the center of the sun. So at the center of the sun, the temperature, right, electron temperature is very high. It's 10 to 6, 10 to 7, 10 to 8 Kelvin. 10 to 8 Kelvin. It's very, very high, right? So it's 100 million Kelvin at the center of the sun. Okay, and here's other region of the sun, so that the temperature change, right, from 100 million Kelvin to the photosphere in this region, it dropped to a few thousand Kelvin. Okay, and here's the corona. Okay, is also a million Kelvin. The temperature. And the y-axis or the vertical axis shows the density of electron and ion, right? The density of electron and density of ion are almost the same, almost the same. So the density of the center of the sun is very high, 10 to 20 something per cubic meter. Okay, and in the corona in this region, the density of the plasma dropped to this region, maybe 10 to 13, 10 to 14 per cubic meter. Okay, so there are different the densities of plasma. In our glow discharge, the temperature is here, maybe 10,000 or to 100,000 Kelvin. It depends on the plasma you generated. Okay, the electron temperature, then electron density, right, could be 10 to 16 per cubic meter. So this is the plasma we can generate in lab. Okay, and and the scientists try to simulate the plasma fusion condition. Okay. Okay, the plasma fusion reactors. Plasma fusion reactors to undergo the deuterium, right? Deuterium and the tritium collision, or the deuterium collision. So those kind of plasma reactors belong to thermonuclear plasmas. So here is the deuterium and tritium collision plasma. Yes, deuterium and deuterium collision plasma. Okay, so the electron temperature is around 10 to 9, right? billion Kelvin inside plasma fusion system, very high electron energy. Okay, and in this figure we can see at the upper left corner it is written as metals. So metal, if we look at the behavior of electrons in metal, the electron can move if we apply an electrical field. Right? So the electrons actually, the free electrons do not belong to any atom, any metal atoms, because they can move freely. So the behavior is also considered as a plasma state in metal, because the free electron can move easily. Okay. So in a piece of metal, the density is around 10 to 27 or 10 to 28 per cubic meter. Okay. So the electron density is very high in a piece of metal. Right? But the energy of electron is very low. So in a conductor, metals is considered as a type of plasma with very high electron density but low electron temperature. Okay, so we can use this figure to distinguish different types of plasma. And in this figure here are several lines. It shows that the bilance. So later in the next chapter, we start with the debilance. Okay. So debilance is a characteristic length or distance. So I mentioned earlier. If electrons and ions exist, right, in a space with a distance smaller than the bilance, then electrons and ions will attract each other. But if the distance is larger than the bilance in a plasma system, there are some shielding effect, so that individual ions will not attract individual electron. So in that case, the electron can move freely, freely when they approach a distance, but larger than the bilance. Okay. So the bilance is also a parameter of plasma. And here is also the figure to show the property of plasma, but this is adapted from another book. Okay. So again, the horizontal axis is the electron temperature or electron energy. Okay. And the vertical axis is the electron density. And in this figure, the horizontal axis use the EV, electron volts, to represent the energy of electron. And in the previous slide, the horizontal axis used temperature, Kelvin, right? Okay. So again, the glow discharge is the topic we will focus on in this course, glow discharge or non-equilibrium plasma. Okay, So again, the electron energy is around 1 electron volt, or a little bit less or a little bit larger than 1 electron volt. And electron density, right, for in this region, 10 to maybe 10 to 7 to 10 to 14 per cube centimeter. So this scale is cube centimeter. So again, you can find different kinds of plasma, different kinds of plasma. Okay, and and on the surface of the Earth, on the surface of the Earth, right, there are gases or different gases, atmosphere surrounding the surface of the Earth. So these figures tells us the pressures, right, the pressure of the atmosphere starting from the surface of Earth and then to the outer space, far away from the Earth. So for example, if we look at this place at the height of the 15 to 40 kilometer, the pressure dropped from 760 torr to 5 to 50 torr. And if it is at a height of 60 to 90 kilometer, the pressure dropped to 10 to minus 1 to 10 to minus 3 torr. Okay, and in this pressure range is equals to around 1 millitorr to 100 millitorr. 1 millitorr to 100 millitorr. So if you generate a plasma in lab, right? 1 millitorr to 100 millitorr. If you generate a plasma by electrical discharge, you can generate this kind of plasma. Okay, so if we look at this place, here is the density of ion pairs, or density of electrons and ion pairs. So in this range, the density of electron and ion pair is around 3 times 10 to 8 per cube meter. And if the distance is higher, to around 200 to 250 kilometers from the surface of Earth, the density of electrons and ion pairs can increase to around 10 to 11 per cube meter, around 10 to 8 to 10 to 11, right? From 10 to 8 to 10 to 11. The electron and ion pair density, 10 to 11, so it's this place, ionosphere. So actually the Earth is covered by a layer of plasma, and this region is called ionosphere. And in the middle picture is the plasma system in my lab. So this is a sputtering system. Okay. So here are two cathode, specially designed cathode, which can be used to sputter metals or compound materials. Okay. So once you generate plasma, you can see the color or the glow coming out. So if you see through the window, you can see inside. the surface of cathode is covered with a layer of plasma. So plasma glows, plasma emits light, okay? And in nature, plasma also the glow emits light. So for example, in the North Pole, right, occasionally you can see a aurora in the sky, okay? Aurora. Okay. So aurora actually exists in this place at a distance around 15 to 40 kilometers away from the surface of the Earth in this region. And you can start see the glow occasionally. And the glow is caused by the weakly ionized gas or weak plasma. Okay. Okay. Any question about today's class? Any questions? No. Okay. Okay, so in a previous slide, we have already known the plasma parameters or plasma properties. Okay, so for the non-equilibrium plasma, when we describe the property or behaviors of plasma, we need to know the electron density, ion density, degree of ionization, electron temperature, ion temperature, and the neutral gas temperature. And then the last one is electron energy distribution function. So plasma is a mixture, right? There are different particles, different species. And all these particles will travel and then collide with each other. So there are multiple collisional process. Okay? So eventually these particles will reach a steady state. And if you generate the plasma by thermal wave, these particles will be also in an equilibrium state. But if you generate plasma by electrical discharge at low temperature, right? Even though the plasma is in a steady state, but these particles are not in thermal equilibrium. They are not in equilibrium state. Okay, and for the thermal plasma, one can calculate the distribution function of the electrons. So the velocity of electrons follows the Maxwellian velocity distribution. Velocity follows Maxwellian velocity distribution. So based on this distribution function, one can calculate the energy of electron. So energy distribution, electron energy distribution, okay? So basically we can use these equations. The energy of electrons equals to 1/2 of m times v squared. M is the mass of electron, v is the velocity of electron. Right, this is the kinetic energy of electron. Okay, and if we convert the energy of electrons to temperature, the energy of electron equals to 2/3 of K times dE. K is the Boltzmann constant, TE is electron temperature. Electron temperature, okay? So usually when we generate plasma, the plasma is not in thermal equilibrium state. Not in a thermal equilibrium state, so that the distribution, electron energy distribution, or the electron velocity distribution will not follow exactly the Maxwellian velocity distribution. So one needs to find out how the energy of electron distribution looks like. And this figure shows the energy distribution of electrons following the Maxwellian velocity distribution. So from the Maxwellian velocity distribution function, we can calculate the energy distribution function of an electrons in thermal equilibrium plasma. Okay, so this is in thermal equilibrium plasma. So the vertical axis is the distribution function, and the horizontal axis is the energy of electron. And here we can use TE to represent the energy of electron, temperature and energy. You can convert them. So in this figure, the maxima distribution function, the maxima value is at this point, and it is equal to 1/2 of electron temperature. 1/2 of electron temperature. So if you want to draw the electron temperature, 1/10 of the electron temperature is around here. It's around here, okay? Or it'll be further. So if the velocity of electrons follows the Maxwellian distribution function, then the energy of the electron follows this curve. So in general, when we describe the plasma, we might say the electron energy of plasma is 1 electron volt or 2 electron volt. But actually, there are a lot of plasma, a lot of electrons with energy lower than 1 electron volt. And there are some electrons with energy higher than 1 electron volt. And it follows this kind of distribution. And this distribution curve is very important in the plasma. Okay. And here, there are two marks. One is the dissociation, the other one is ionization. Okay. So if you use hydrogen as your working gas, right? Hydrogen is a diatomic molecule. So the dissociation means that hydrogen molecules become hydrogen atoms. And this energy is required to dissociate hydrogen molecule to hydrogen atom. And the other one, IZ, is ionization. So you need an energy higher than the dissociation energy to ionize hydrogen atom to proton and electron. Okay. So tomorrow we can start from this figure to see how important the electron energy distribution function is. Okay. Any question? Okay, then class dismissed.